My name's Darren Buttle, and I'm Head of Embedded Software and Safety Engineering at ETAS. And I'm going to talk today about ASCII Developer. ASCII Developer is a tool that we've had on the market for about 20 years now. And it's a tool for building high-integrity software and doing code generation for deeply embedded systems. To give you a rough idea of where we are, we're just about halfway through now, so coming up to lunch. We're here doing graphical and textual software development with high-integrity code generation in ASCII. And we've seen this one before, and Bernard talked about taking ISLA A and ISLA B. We've talked about Papyrus. We've talked about pure systems with pure variants. And we're going to focus on software component implementation here. And in particular, we're going to talk about this tool called ASCII. So I'm going to talk about three things now. The first thing is I'm going to give a quick overview of what ASCII Developer is and what it does, and what kind of problems we're trying to solve with that. Then I'm going to cast that into the AutoSAR context, so bringing us a little bit back from more abstract things into, OK, how do we put AutoSAR software components together? So I'm going to talk about how ASCII fits together with the AutoSAR workflows. And if I can make my keyboard work. And we're going to look at a bit of code. We're actually going to look at a little bit of code called ESDL, which is the notation that we use inside of ASCII for describing systems. So the first one of those three things is ASCII. Who's used ASCII before? Anybody? OK, right. OK, so some of you know about ASCII and some of you don't. So in a nutshell, it's an advanced software component engineering tool. We like to say advanced in front of everything. So, and this is what the tool looks like on the right-hand side. So like a lot of modern ETAS tools, it sits in Eclipse. It allows us to basically build software in a variety of notations. The first notation and the technology that underpins all of ASCII is a thing called ESDL, so Embedded Software Description Language. And that's sort of the child of Pascal and C with a bit of classes thrown in, so a bit of C++ classing thrown in. And the idea behind ESDL is to make software easier to write, reuse, and maintain. So much more easy to use than writing things in C and hacking around bits of C and putting hash includes and hash pragmas everywhere and this kind of thing. And you can see a bit of ESDL on the right-hand side here. It looks a little bit like a normal C family programming language. ASCII also has a couple of graphical languages, and we use those graphical languages for people who don't like to write code, so particularly people who are coming more from the sort of engineering controls side of things. So we can draw pictures in ASCII, and a picture in ASCII is actually a program. So unlike something like Simulink, where you've got a data flow diagram and you're feeding data in, calculating and flowing data out, an ASCII picture is just a graphical representation of a program. So we've got things like control flow in there, we've got assignments, we've got statements. It's basically just a different representation of that ESDL meaning. And like every other tool, we've got some way of doing state machines. We actually use some technology from a firm called Itemis, who will be speaking a little bit later. So you can do state chart tools, and we use that as our graphical representation for state charts. And both the graphical block diagrams and the state charts, they're all represented, and their entire semantics is held in ESDL. So the only thing the code generator ever sees is a bit of ESDL code, and it translates that to C for you. The code generation technology is pretty advanced. We spend a lot of time trying to make that very low overhead, very high performance. So typically people who use ASCII will build a complete ECU in ASCII, the entire application software. So it's not unusual to find people generating sort of between 2 and 4 gigabytes of code out of ASCII. And they need to have turnaround times that are 5 to 10 minutes for that. So we tend to focus on basically being able to integrate in a really fast turnaround system with things like continuous integration. And we generate MISR-compliant C code out of it. So currently MISR 2012. Somebody might want to ask me what that really means later. It's independently certified. We do ISO 26262 ASIL-D. We've done that for about 4 or 5 years now. And we do 61508 SIL 3. if anybody here travelled to Munich on the train, we do 61508 basically for the company that builds the braking systems on the German high-speed railways. So that's built in Ascot. So we started doing a lot of the safety work back in 2002. We're the first people ever to certify a code generator. And it's been around for 20 years, and we've got about 500 million ECUs on the road that run Ascot-generated code. And in terms of the rest of the tooling, it fits with quite a lot of other things. So there's a lot of the ETAS tools it fits with. So things like Skoda and Conga that Marcus mentioned earlier, things like our experiment environment. We can do bypass, we can do rapid prototyping. We can work with ISILA A and B that Bernard mentioned. We can do co-simulation. We can spit out Ascot models and package them up so that they run in Simulink. So we can generate basically an S function, and you can then test that against your plant model. And we can just generate code that you can compile up and run it on a bare metal ECU with no additional support other than an AutoSAR or OSIC operating system. And it talks AutoSAR, and it talks FMI, and it'll talk app for MC if you're doing things like multi-core distribution and things like that. So Ascot's about essentially software-focused algorithm development. So it's not about sort of designing control strategies. It's about actually, I know what I want to build, and I want to get that into code, and I want that code to be correct. So what Ascot actually embodies is what you call good old-fashioned software engineering. So anybody that's good and studied computer science at a university knows about all this stuff. So we've got essentially an object-based model of reuse in there. So in Ascot, you create classes, and you create instances of classes, and classes can have various variations in them. There's a type system in there, so we can say not only is that an integer, but it's an integer and it runs from -50 to +50, and we can use that additional information to be able to do things like automatically generate defensive coding checks in your code so you don't have to write them yourself. It's got an integrated real-time model, so we have a single publisher, multiple subscriber model, which dovetails very nicely with the AutoSAR sender-receiver model. And we always assume we've no dynamic storage, so we're targeting deeply embedded systems here. There's lots of other things that will talk about this, lots of other tools. One of the things that we do quite a lot of, and this has come from sort of 20 years of serious production experience, is that we spend a lot of time building in points of variation into the software. So to be able to essentially do some kind of product line engineering and roll that through an object-based development model. So we can do things like have variant coded data. So let's say you build an algorithm, and in one ECU you want it to run on the floating point unit, and let's say it's an SH2, so it's got a double precision floating point unit. You can target it for that. Let's say you pick a tricore, that's a single precision floating point unit. You want to basically cast all those calculations into single precision floating point. And let's say you want to deploy that algorithm on a star 12 with no FPU and it's 16-bit, and you want to quantize everything using fixed point calculations. You want to do that without touching any of the code. And what actually Ascot allows you to do is to take your existing model, your algorithmic part, which is not going to change, and then define basically multiple different variations of how you're deploying that into the target hardware. And a variation might be about how numbers are represented. It might be where data is stored. So is it in near RAM? Is it in far RAM? Is it in Z data section? You know, these kind of things. Is it on core A? Is it going to be core B? How do we calculate about things with costs of fetch and things like that? So we can calculate all these variations in here. We can also make code easily portable. This is kind of important if you're using Ascot in a non-AutoSAR context, because you want to, again, write the code, but you want to deploy it on multiple targets. But you want to be able to define those independently of the code itself, because otherwise you end up with hash pragma sec var star.bss somewhere all the way through your code. And then you come up with a new target and a new piece of hardware, and now you have to do all that again. And in Ascot, we abstract that. You give us some synthetic names, and we just roll basically definition file in at code generation time. And we can also make that work with AutoSAR, as we'll see later. And we can package this up for different deployment platforms. We take the algorithm, let's stick it into an S function box. Take the same algorithm, stick it into a thing for doing host PC experiment. Take that same algorithm, pack that as an FMU for using in co-simulation. Take that same algorithm, pack that as a bypass function, either for internal or internal target bypass. And take that same function and pack it into an AutoSAR box so that it connects up to the rest of the AutoSAR architecture without changing any of the code that you've written. So we do all this with essentially mapping things and mapping things into different sorts of abstractions. And we have the right tool for the job. You can build ASCII models in multiple ways, which I touched on before. We've got the textual models, and we've got two sorts of graphical models. And we can also make that fly with C. So you can call C from ASCII. You can implement parts of your ASCII function as actually a native C function. You can make that a C function that we simply call over a method interface, or you can embed that C code in our generated code as well. So that's basically what you can do. In terms of the problem we're trying to solve, so let's say you're this guy. So you're Mr. ETAS and you're thinking about writing a piece of software. Actually, there's quite a lot of noise that you have to think about just in terms of writing a normal program if you're going to hack that together in C. And there are all these kind of things. So yeah, you write an array. How are you going to make sure that you don't run off the end of an array or index below the bounds of the array? How are you going to make sure concurrency control is working properly? What about working with fixed point? Are you going to use some libraries? Are you going to write that yourself? Are you going to do that by hand? What happens when you divide by 0? What happens when you do an underflow or an overflow in a calculation? How is all that going to work? Yeah, you have coding standards. Yeah, you probably want to do MIS because you're good boys and girls, but you might want to do something else there. You might want to sort of not really want to care about how big a piece of memory is that you pack a piece of data in. You know, it's a speed. Yeah. How many bits do I need for a speed? Well, I don't really care. What I'm interested in is, okay, what's the bounds of my speed and what's the resolution of the signal that I've got? Whether it's a 16 or a 32-bit value, I probably don't care about in the software engineering level. And yeah, the compiler's going to screw me over. It's going to change expressions, and I'm going to get different calculations when I compile it with different sets of options and this kind of thing. And we're going to code all that up in C, and we get the fire extinguisher out, and we start debugging it. Okay, so basically it's on fire, and we now need to start finding all those bugs. So it'd be a good idea if we could stop putting those bugs in the first place, so we don't have to spend a load of time taking them out. And actually in the middle of all this, there's this job, which is the one we're actually trying to do, which is to actually build our software and solve the problem that we're intending. And all that other stuff's just noise. That's just because we're implementing it in C and it's crap. So what we're going to try and do is to simplify all this kind of stuff and allow this guy to focus on that problem and automate all those other things around it. And that's what ASCII does. So it allows engineers to think about actually engineering the problem, and we give you a nice notation or a set of notations to do that. We allow you to code that up in ASCII. ASCII turns the handle, thinks about all of that stuff for you, and generates some C code. And that's what when we talk about high integrity C code, we're putting in the defensive coding checks in here. We're checking that that model is right. We're making sure that if we need to check something at runtime, we're only doing that where it's necessary. So if we know that we never divide by 0 in a range, we can make sure we can align the division by 0 check out, with the option of trying to make the code as small and as fast as possible. And all of that's designed to work the rest of your software process, so it fits in the Eclipse ecosystem. How do we store my files? Well, it's just text files on a disk, so you can easily version control them, you can diff them, you can manage it really, really easily. Typically, nobody mentioned this, but a typically ETAS customer using ASCII has got about 100 tools in their tool chain. It's astonishing, the complexity of these kind of things. And actually, all they want out of the end of that is some software and a bit of meta information. Where are the symbols for calibration? Maybe I want a bit of documentation out there, this kind of thing. Right, so far so good. What the hell's that got to do with AutoZAR? If we think about AutoZAR, we've essentially got two things. We've got an abstraction, that's the virtual function bus in AutoZAR world, and we've got an encapsulation, basically a load of mechanisms and a load of code that we're going to generate to make that stuff work. So we're going to have the RTE in there, we've got the operating system, and we've got the communication stacks. So basically, I've got that abstraction and this encapsulation of that abstraction. And what I'm going to try and do with ASCII is pack stuff into these boxes. And we know how to build those boxes because Bernard showed us earlier. So if I take a software component, it looks a bit like a PlayStation here. But I've got some inputs on the outside of it, some external behavior. Data comes in, data goes out, function calls come in, responses to function calls come out. Pretty easy. And it's got some internal behavior that captures all the various things there. It's got a set of runnables, so basically threads of execution. Those communicate with those ports. They can communicate internally in lots of different ways. So whether I'm reading it in an expression or whether I'm reading it through a function call is a little bit different. I've got events. I've got per instance memories. I've got internal variables in all of that. Okay, so and what I'm trying to do is to try and simplify how we build all of that stuff in the center of this box here. So, sorry. And the thing that's missing is essentially filling in those runnables and defining how those runnables communicate with the rest of that software component. And that's what we're going to do in ASCII land. So basically what AutoZAR gives us and what we get from ISLArray is essentially the preschool coloring phone book. We get a nice black and white picture, and we need to now color that in somehow. So what we're going to do with ASCII is essentially to take these ASCII crayons, and we're going to color that in and produce an ECU. That's what we do in ASCII. Okay, so in terms of the simplified process then, we're just going to write a normal ASCII program. We're just going to do that really, really simply. We're then going to map that into an AutoZAR software component model, and we're actually going to see how we can do that auto-magically. We're going to build this and actually generate this. And then finally what we do is we generate C code, and we generate some XML code that defines all that internal behavior, so it all fits together. And this is really nice because I've got a single source for what the functionality needs to be, and I can keep always this AutoZAR model and this C code in sync together. So let's have a look at how this works then, and let me move to my ASCII version. Okay, and I probably need to, let's try it this way. Let's see that. Right. So here is ASCII, and here is an ASCII model written in ESDL. So this is back to our light switch model. So the first thing is you can see on lines 4 to 6 that here we've got some type declarations here. So we've got the light position. Well, that's an enumeration, and it's got 3 enumeration literals. It's off, on, and it's automatic, so that we've seen before. We've got that light intensity, 0 to 100, and we've got that headlight status, which is off and on. Okay, and that's a type declaration in ESDL. You'll notice that on line 5, we've not specified how are we holding that. Is it a float? Is it an integer? We don't care. It's just a real number with a range on it. And then what we have is a set of interfaces that are how basically ASCII can communicate with the external world. So it's got a channel coming in that defines the light. There's a switch on there, and there's a light intensity on there. And they've got some nice values. So I can say basically the light switch is position off, and the light intensity is, if I go here, is I can do nice things in ASCII like, okay, I've got a light intensity, it's a type range, just give me the first value of that type range. So if I define that, for example, like a Swedish car, the lights might be on all the time, and it's going from 10 to 100, I don't need to go around and work out that I'm pulling value 10 rather than value 0 out of there. I can just say, give me the first value of the range. And then I've got the headlight channel where I'm going to read that status and set the default value. So we also said we've got an automatic mode. So back to this morning when we talked about variance, this is one of my points of variation. Do I have an automatic mode? So I can define that here with my automatic mode, and then I can build the rest of my controller here. So I'm going to build that as a class, a single instance class. It's going to read that channel with the light in it. It's going to write that headlight. It's going to have a value that I'm going to set as a calibration value. So that's why it gets the word characteristic here. I'm going to put that in the calibration space so that I can modify it post-code generation, and I set that value to 60. And then I can actually write a method that does all the manipulation, and you'll see that this looks very similar to what Marcus showed us. There's just a single thread of control that's calling, that's looking at the switch. Is it off? Is it on? Is it automatic? If it's off, we switch the headlight off. That's on line 42. If it's on, we switch the headlight on line 47. And if it's automatic mode true, and only if it's automatic mode true, we calculate the required status based on the current light intensity. Is it less than that threshold, in which case it's off? Is it more than that threshold, in which case it's on? And we can generate code for that, so I can do run as code generation here. And hopefully, other than it complaining about something, I'm running development software here. It will generate me, hopefully, some software down here. Chug, 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 chug. There we go. And it generates me a bit of a light controller here. There's my calibration constant. It's plugged in const volatile, because I'm going to modify that with calibration. And there is my actual ASCII code. These are my reads of my values. So this is creating a cache for all that data that's concurrently shared. This is going to populate that cache. It's going to do these calculations here based on those values. You can see I've now got my switch here for my mode of, okay, is this a variant? Is it enabled or not? And then it's going to write that out at the end. Okay. So far, so good. But none of this looks much like AutoZAR. So what we can do is we can say, okay, well, what I want is I want a new ASCII to AutoZAR mapping. Finish that, and let me open that. This gives us then automatically, we've created basically a skeleton of that application software component in a language similar to RTOP. And we're going to use that to generate the IRXML. And then we've filled that with mapping. So we're saying, okay, map this ASCII signal here to this AutoZAR interface here, and map this runnable entity in AutoZAR to this model in ASCII. So if I hit F3, I can go back and see that's exactly that method there. And then what I can do with that is I can do run as AutoZAR code generation, and I can get essentially a different model generated here. And that's going to come out here. Chug, 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 chug. And now I've got something that looks a little bit different, because I've now got basically, let me do this. I've now got code that's actually now, so this is my regular ASCII code, and now this is my AutoZAR code. It looks a little bit more AutoZAR-like now. So I've got the right function macros around that method, and you can see that rather than doing these reads and writes by ASCII native code when we're running without an RTE, actually what we're doing is we're generating those RTE reads and writes calls there. Looks a little bit simpler. So we've now taken exactly the same model, and all I've done is we've just done 2 code generation steps, one for straight C, one for AutoZAR. And what I've also got in here, and you can see this down here, I've actually got the generated software component. So if I look at the source code of that, there is my, let me close everything else, close all those. I've got my software component here, and you can see that I've got my interfaces defined, and I've generated all my internal behavior and kept that in sync with how I'm reading and writing that in my ASCII model. So I don't need to maintain this by hand and keep going around that loop all the time. Right, so that was a very quick tour of what an ASCII model looks like. So just in terms of summarizing then here, in summary, ASCII, we've got a long proven in use product. We're trying to prevent bugs by design through the use of ESDL to try and engineer our way out of avoiding certain categories of bugs. Typically those kind of silly little programming bugs, but also giving you a little bit more structure and control over your models. And we've got a simple on-disk text format. If you open ESDL in Emacs, it looks exactly the same as it does in Eclipse. It integrates into Eclipse nicely, and we can easily package all these models for different use cases. So simulation, bypass, AutoZAR, and a bare ECU. And that's what ASCII does.